know whether a building and its components can withstand extreme winds and devastating storm conditions. And we do mean extreme winds. Today we'll give you the first ever look at a storm simulator that was $4 million and 4 years in the making. We're here at the University of Florida with Dr. Forrest Masters, his research team, and the door manufacturer who helped make this project a reality. The simulator is designed to test commercial and residential structures and can simulate an E4 tornado or a Category 5 hurricane. The test structure can produce 460 pounds per square foot and is 24 feet wide by 17 feet tall. Before we show you the machine in action, let's find out how this research, which could revolutionize the industry, came to be.
Henry Upjohn, CEO and chairman of Special-Lite, a high-end entrance systems manufacturer, wanted to build a machine where you could test a variety of materials, even the side of a house or a curtain wall system, under hurricane or tornado conditions. It was so important to this engineer that he was even willing to fund 3/4 of the $4 million project, as the research done here will allow his company and others to develop additional innovative products. Masters says Upjohn was the driver of the mechanical engineering behind the system.
So what do you hope to gain from this research? What was your main goal?
We've been very successful in exterior building products, and I had heard from a friend of ours in the insurance industry that actually goes in right after hurricanes. He came to us saying that we're getting a lot of damage in, say, Category 2 storms, where the code around there is Category 3 or 4 or 5. He felt that one of the issues was that the current ways that they evaluate hurricane doors and exterior building products for hurricanes were probably they'd been much better than anything else in the past, but really were not giving them the feedback that they needed. I had met Forrest Masters through this insurance friend, Ben Hardesty, and he had expressed that, what we really need is a way to evaluate products based on actual hurricane experience. So the idea was to build a piece of equipment that we could put large pieces of building equipment in, the whole side of a house, or man doors or whatever, and play back the hurricane on the door,
right, and
see what happened. And one of the things is they normally put continuous pressures on things for a while, and then maybe cycle it a little bit. And actual hurricanes, the wind is just, coming and going. The pressure is changing very quickly,
right,
and you can put a door in a pretty mild situation and then just have it shaking like that for a few hours, and it begins or falls apart or fails. So this was right down my alley in terms of my experience, that if you really want to know what you're doing and you're not just going to use the general rules in the industry, especially when it's changing, you need to build equipment that lets you evaluate what's really going on and then see how that measures up against the current stuff.
Dr. Masters has been chasing hurricanes, so to speak, since 2004. His research has been based at the University of Florida, where he serves as Associate Professor of Civil and Coastal Engineering. He has received 20 grants from state, federal, and private sources, and his field research includes 27 experiments in 25 named storms. Dr. Masters was eager to get to work on Upjohn's vision. Many in the industry may know him for his hurricane simulator that can test windows and doors and simulate hurricane conditions. In fact, USGlass editor Ellen Rogers was here in 2008 to profile Masters and his work.
So what was your first reaction when Henry approached you about this project, and what were your expectations going in?
I was excited. Early on, I learned from him that they were really looking to put the science first, and they wanted to transform an industry, not just the way they do things, but they wanted to take an entirely new look at how R&D can happen, in the context of designing hurricane-resistant products.
What effect do you think this will have on the industry, building products industry, but also if you can speak to the door and window industry also, how will it change how products are developed?
So I got my start after the 2004 hurricane season, and at that time, there was a lot of finger pointing going on, and I remember very specifically the product manufacturers, were in the limelight, and even since then, I've heard a lot of discussion that somehow product manufacturers take shortcuts to put their products to market. And having worked with more than 50 different industry groups, I don't generally think that's the case. The missing piece, I think, for them is being able to both visualize what happens in a storm and how that affects their product, and also having the means to quantitatively analyze what's going on. I think this will inspire industry to push boundaries, to try new things, and ultimately, it'll give them the confidence that they need to keep innovating.
And you don't just do research here in the lab, right? You follow the storms as they happen.
That's right. So, a lot of the inspiration for this work comes from seeing the aftermath of storms, and also conducting field experiments. So, since 1999, I've been heavily involved working in the storms, collecting wind speed, wind pressure, and also wind-driven rain data. And so we actually go out in the storms right at the landfall point, we record this information, and then we bring that back here to help calibrate these systems. Mm-hmm. So we're trying to sort of leave the model out and go directly from what we see to what we get. Power is delivered to the fan assembly by this 1,800 horsepower diesel engine. This engine came out of a generator set. It's not a traditional application. Originally we looked at using electricity, but it was so expensive that we decided to go with the engine. So it's actually direct coupled into the fan assembly over here. If you just look over here, you can see the drivetrain. That part that's spinning is the air clutch. So that's actually how we couple the power right through here. The engine's off and it's still spinning. You can see it from this side. So this takes a few minutes. Once we disconnect all the power system, it takes a few minutes for the fan to stop spinning. So this is the fan. This fan assembly can produce 460 pounds per square foot of pressure at about 100,000 CFM of leakage. We're standing in the area where the main control is located. So if you follow me over here, you'll see it's a hydraulic system. Inside this red cage, we have a louver damper system. The louver damper does this. There's 4 paddles in there. It can open, shut, and close in 0.16 seconds. It's incredibly fast. In designing this, in fact, it was decided to use printing press bearings. They're pre-stressed bearings. It's a high degree of tolerance. The system is completely balanced. So we have about 100 horsepower driving this system. So this large rectangular assembly unit actually has 4 components. The gray part is a large reinforced concrete frame. We call that the airbox. There's an outer reaction frame here. You'll notice the columns are very wide, and that's because when we put in large systems like this, they develop something called catenary force, which means that it's trying to pull on the sides. In some cases on these systems, they can pull as much as 10,000 pounds per foot, so substantial. So that's why we have these really beefy sections here. We have an internal secondary frame that goes in here, and this is custom built to match the specimen side. So the specimen goes in here and fills up this space. If we want to, we can take out this secondary frame and we can accommodate something that's 24 feet wide by 18 feet tall. So we get a very, very large specimen in here. And here you can see this is the actual pressure chamber, standing in it now. So we drive air into the box through this guy, and then we pull air in through this way. So we can run tests in either positive pressure or in suction. So we're standing in the control room. This is where all the command and control takes place, where we monitor the systems. This is the brains of the operation. So here we're looking at the safety systems, the power distribution systems. Over here at this console is where we operate the equipment, and we also monitor what's going on. You can look right out here and also see what's happening with the specimen. This is 1-inch Lexan, so if anything flies loose, it should be okay. This console is where the action really happens, though. You can see all the various subsystems All these green lights have to be on before we can operate the system. So we're monitoring temperature, we're monitoring vibration. These are important issues, especially with systems this large. Over here, we have, the system has 5 different dampers. 4 of them, 1, 2, 3, and 4, basically control the airflow. So these can either be open, closed, or manually adjusted. This is the louver valve system, the big red control that we saw. And then over here, we have different settings. So we can either perform a wind test, a vacuum test, or a pressure test. What's particularly interesting about this system is that it really relies on traditional technologies to make the whole thing go. This system is entirely relay driven, which means it's easy to troubleshoot. The whole system is also entirely analog, which is a very unusual thing these days. But it gives us greater control, and the system runs very quickly. You get faster response times as it's configured.
So is this simulator the only one of its kind in existence?
This simulator was born out of the idea of work by the Building Research Establishment back in the 80s and early 90s. And they developed a system called Brer-Wolf, which is a much smaller system. This has 1,800 horsepower. That probably had a few, maybe 10 horsepower maximum. The University of Western Ontario developed the second generation system in the early 2000s. So there are, sort of predicate technologies that are out there that this is derived from. However, a system like this that can simulate these pressures at this kind of leakage rate or airflow, really, to our knowledge, doesn't exist. So, we think this is a tremendous step forward.
Masters and his team did the first ever video simulation when we visited UF. It was impressive, to say the least.
If you imagine you went back to, say, Hurricane Francis or Hurricane Ivan and Ike, and you took a pressure sensor and you stuck it on the side of a building and it measured pressure 2 or 3 times a second, and you left it there and you came back after the storm and you had this pressure sequence, the basic idea is this system can replay that. What I'm really excited about is I think this represents a real opportunity for manufacturers to come somewhere and try out their ideas. Create a real hurricane environment. We can install their system in in-situ conditions.
And you said you could work in things like installation errors,
exactly,
work in real-world conditions.
Real-world conditions. So we take all this data, and separately we have a computer model that we're running, and we bring this in and we validate the computer model. We refine it until it matches this, and at that point, once we have a high confidence in that model's ability to predict structural performance, we can make changes to it if we're trying to do product design. Or we can cause, say, installation errors or construction defects that might occur and see what the effect would be on the system. So you can look at things like, look at redundancy.
So it's been 4 years since it started. So where would you describe where you are in the process now?
Well, today marks a really important day. We're really turning the corner now to begin actually the experimental component. We've already been doing the computer modeling, working on different systems. So looking ahead, it's really going to be about refining that process, learning how to do this quickly.
And you can help companies with different types of building products, doors, windows, the glass systems in those products as well.
Yeah, really, any vertical surface, this is perfect for us. Well, it's a large cladding or component system. This is ideal. We'll have to go back and review the footage. So there was beam buckling, and I think we lost some rollers. So which one came first? We'll need to look at the video footage to tell.
It is evident that the research done here could have a dramatic impact on the fenestration and glass and glazing industries. I'm Taffera at the University of Florida. Thanks for joining us for this special feature, and look for more of our storm coverage in future issues of DWM and USGlass magazines.